just a reminder that I am not using Zoom to share, but just the camera. So you have to pin me, so it keeps me on top. Okay. Let's go. Multitasking on a Commodore 128. So I'm going to start a bit with an introduction about multitasking. I am going to keep that very short, but I do need to tell a few things about what makes for a multitasking system and what the problems are on a 6502 CPU. Because there aren't that many multitasking systems on a 6502. However, there is a very old one going back to the 1970s, and it comes from a famous company, Commodore. I will get to that. So this is a short agenda of what I am going to tell. So a little bit of history, a bit about my operating system. I'm going to show a little bit from my operating system, and I have some frequently asked questions because people are asking a lot about this already. So the multitasking basics that I need to explain. First thing is we have a single CPU on a Commodore 64, Commodore 128, Amiga, doesn't matter. It all works basically the same. What you have to do is you have to divide the CPU time among the tasks that you want to run. And the easy way to do that is to have an interrupt every so often, and that interrupt does something that is called a context switch, and that context switch says like, okay, I have the next task, that is this, and I'm going to schedule that, and I'm going to leave it for a little while so it can run, and then I'm going to interrupt it, look for the next task to run, and so on. So that is how CPU time is divided among tasks. The second thing is we have memory, and memory on a modern computer is, well, it is virtual, and that makes a lot of things easy. We can set up an address space for each task that we want to run, and we can make it such that it only sees its own things, it only sees a kernel that it can call to, and it doesn't see any other tasks unless they want to share something. This is something that those who have a traditional Amiga, 68000 based Amiga, know that is not really supported on a 68000. It is certainly not supported on the 6502. And on a 6502, we have a very specific problem with it, and that is the stack. And why is this a problem? Well, on the 6502, you have a stack of 256 bytes, and normally you can't really change that. It is there, and well, it's the only thing that is there. So you can't have normally on a 6502 a separate stack for each task, and that is what you really would want because of the size, but also because you basically use the stack to an interrupt uses the stack to store some information, and it would be ideal if you can then assign a different stack, pull information from there, and use that to start or to run the next task that you have to run. On normal 6502, this is not possible, and this is the nice thing about the Commodore 128. It has a memory management unit, which makes this possible. And that is also how this got started. Basically, I wrote a multitasking operating system for the 64 about 30 years ago. That was a proof of concept, never got anywhere beyond it because it's extremely inefficient. It can be done, it can work, but yeah, you have to copy a lot of data around to make it work, basically. And there are systems that do this, but there is a different solution for it. That is what Commodore used. We will get to that. Um, but anyway, the Commodore 128 makes it easy to have a different stack for each task. And that is really what makes it possible to implement an efficient multitasking operating system on this. The next important thing to know about in a multitasking environment is devices. And the problem is very simple. You have, for example, a disk device, and you can't have two tasks trying to talk to the disk at the same time because they may do conflicting things. They may try to send the head to the first track or to the last track, and they will interfere with each other. So you have to do something about that. And the last thing that I need to explain is tasks, processes, and threads. Normally, when you talk about a multitasking system from an end user point of view, you just say, like, I want to start a program, and that program is a task because I'm doing things in it, and I don't care how that really works. From a user point of view, you just see a task that you can run or a program that you can run. Underlying, there are a few things happening. On a very simple multitasking system, you just have processes, and that's it. On a slightly more advanced system, you have processes, and each process has a number of threads. And what is the difference? Well, we will get to that. So going back to the CPU, um, the time that a process or a thread actually can run is called the time slice. And it's a limited amount of time, and after that it will get interrupted. And that is why interrupts are very important in a multitasking system. Another thing that is important when looking at the CPU is ensuring that the right task gets to run. So you have to somehow assign priorities to tasks. So looking a little bit more at processes and threads, a process is really just something administrative. It is a container that contains resources, and resources can be memory that is assigned to the process. It can be one or more threads that actually get CPU time. And an interesting detail of that is that when you start a program or a task on a multitasking operating system, it can internally multitask again. So you often see that in modern systems when the user interface and some background process that is doing, for example, file copying or calculations or so on, those two things happen at the same time for the end user at least. And normally that is implemented by putting both in the same process and creating two threads. One handles the user interface and one handles whatever needs to happen else, the calculations or whatever. If you look at memory, I already mentioned that 6502 has no real concept of virtual memory. But it is important to understand that there can be private memory that is for a specific process or a specific thread only, and you can have memory that's shared between processes. Um, Memory that is only used by a specific thread is called thread local storage. So it is only for that specific thread, and it shouldn't be shared with anything else. Another thing is that each thread needs its own private stack. Now, those two things are possible on a Commodore 128. They are not possible basically on any other 6502 machine. And again, that is what inspired me to delve into this operating system idea. Um, Devices, you could imagine having a private device that is only for that one thread. You can also have shared devices like these devices that need to be shared between different tasks that are running. And for that, you need something called arbitration. You need a kernel, and the kernel needs to say, like, you get access to it now, and something else has to wait. So if we look at the history of multitasking on 6502 CPUs, well, one thing we basically all know, and that is having some music play while something else is happening. And the way that works, those who write 6502 code or things for the C64, C128 know that you have an interrupt and you let the interrupt call some music routine, and then it finishes doing a little bit of work and it returns to whatever other program is running. That is a very primitive form of multitasking. Um, I wouldn't really call it multitasking, but it gives the impression, at least. The next thing on the list is the 15XX drives. And those are a really interesting story. I'm not going to delve too deep into that. But something to know is that the 1541, for example, the firmware on it, is actually a modified version of the firmware of much older drives. And those older drives had two CPUs. Yeah, Commodore made multi-processor systems in the 1970s. 1541 only has one CPU, and it needs to run the code that was originally running on two CPUs. So what it really does is it switches between what was running on the first CPU, and then it switches to what is running on the second CPU. One handles basically the drive mechanics and so on. The other one handles all the communications. And it switches back and forth between those two. And this really works like a very, very primitive multitasker with actually two tasks. Um, both tasks have their own stack. And how does it do that? Well, it really splits the system stack in two stacks of 128 bytes. And yeah, that is enough for a 1541. You could actually take that a step further and create four processes and give each 64 bytes, but you can't take it much further than that because, well, 64 bytes is not that much stack, and call a number of subroutines and get an interrupt and your stack is full, and that is a bit of a problem. Then you start overwriting the stack of another process. So it works, but very limited. Then at some point, don't know exactly how long ago, somewhere 20 years ago, 15 years ago, or thereabout, someone made something called Linux, which is a Linux-like system for 6502. And this is portable to the 64, to the 128. It's really cool. It is very, very functional, amazingly so, but it is very inefficient because it needs a big stack. And how does it do that? Well, it simply copies the stack to a piece of free memory when the next task has to run, and then it copies the stack for that task on the place where it needs to be. And that means a lot of copying of data, and that is expensive and slow. So really cool, really, really functional, and really inefficient. And that brings me to my own project, OS 128, which is a temporary name, I think. Not sure. Um, at least it is the name I'm currently using. And I solved this in an entirely different way, which is really Commodore 128 specific. So going a little bit into OS 128, you have a few components that are important. One is the scheduler, and the scheduler determines which task can run at which moment. It uses a fixed length, time slice length for each task. That is at this moment, let's see, 6401 megahertz cycles, but it runs at 2 megahertz, so say 128,000 cycles. And after that, an interrupt occurs and the next task will run, and that is based on the priorities of tasks. Now, there are four priorities. One is time critical, one is high priority, one is normal priority, and one is low priority. And each priority has its own run queue, and those only make things more efficient because I only have to look at the critical queue to see if I have to do anything. I don't have to search all tasks to see if there is anyone critical, and so on. When there's nothing critical to run, it goes to the high priority and so on. There is something funny happening there, something I stole from another operating system called OS2. Um, when there is no critical, when there is a critical task to run, it won't get to running a high priority or so on task. However, it will still look at those queues and it will pick the first item from each queue and move it up one queue. But only if that queue didn't get time during a time slice. And what this guarantees is that every task will at least get some time every so often, even if there are a lot of critical tasks. And that is that brings us to the next point, preemptive behavior. One of my goals with this was make a system that is really responsive, no matter what you do. And that means also during I/O, it must be really responsive. Also, when there are lots and lots of tasks running, it must remain responsive. That was a very important goal for me. Now, the features that I use from the 128 are the relocatable zero page and the relocatable stack. This means that in a few cycles I can assign a different stack and I can assign a different zero page. And each thread that is running gets its own zero page and gets its own stack. And that means that the context switch only takes, well, a couple hundred cycles, really. To compare, a context switch on Linux takes anywhere between 100,000 and up to 1,000,000 cycles. So on a 1 megahertz system, a context switch could take up to a second on Linux, and on OS 128. Looking at it, a worst case scenario, it would be like about 500 of a second. So you can have 20 slices in a second still, even in a worst case scenario. To make I/O possible and to ensure that it is not too much interfering, we need buffering. And that means all I/O is buffered, and all those buffers must be in memory all the time to ensure that when a device has some data, that we can write it to a buffer, and that the task that actually needs it, when it actually gets time, it can just access that buffer, and it doesn't have to access the device directly. This also means that the kernel can decide when that task gets to run again. It only gets to run when the buffer it is waiting for actually has data for it. So with all that said, we get into a few peculiarities because on a C64, C128, we have all those nasty IEC devices. And the problem with those is that they need a lot of attention. Basically, you need to talk to them all the time, and it's pretty time critical, and it just doesn't work for this. That means that I can support a 1541. I can support a 1571 because it can use fast mode. And fast mode means that it will generate an interrupt when it has data ready, and that I can respond to without having to monitor it all the time. So when looking at what kind of storage I can support, it will be all burst mode devices, including a CMD hard disk, but it won't be any 1541, 1540, and currently also not an SD2 IEC. I'm still looking into supporting Jiffy DOS. I have code for it actually. It supports a kind of block mode, which would make it efficient enough, hopefully. So that's too bad, but that's the way it is. Also, we are missing some functionality in the MMU, and it's kind of funny. About 2 years ago, I had a long discussion with Bill Hurt, the lead engineer for the Commodore 128, about this. And he was complaining about no one using the stack relocation, zero page relocation. And I was explaining what I was planning on. I hadn't started on it yet. And we started discussing what he really wanted to do. And he really wanted two things. That is shadow registers, which would make interrupts lots more efficient, and some kind of supervisor mode, so you can have memory that is read-only, even if it's wrong. Well, sadly, we don't have that. So that is really missing in this whole setup. That means we also don't have virtual memory, but we do need swapping. And I will explain why, but for swapping, the only reasonable way to do that is to use Commodore's RAM expansion unit, or a clone of it. GeoRAM, sorry, no go. It has no DMA, it isn't fast enough. So an REU, Ultimate 2 Plus, or such device, or the ROD device with the proper firmware should also work. So looking a little bit at how OS 128 actually runs multiple processes. If you look at a 128, you have two blocks of RAM, each 64K. And looking at it, this is all, well, the first column just says the address range. The second says what is in there for RAM block 0 and for RAM block 1 and for the kernel. The kernel is a function ROM. It's always in ROM. And that means that it can overlay whatever ROM is active at the moment. So you see one process running in bank 0 or block 0, one process running in block 1, and every other process is in the RAM expansion unit. And what I do is when I need to swap in a new process, I copy the current one to expansion RAM, and I copy one from expansion RAM to system RAM. To prevent that from happening too often, the first thing I look at is there a thread in the current process runnable? If not, then I switch to the next process. So if you have a 256K 128, which exists, well, you can expand one. I can use all four blocks of RAM. So you can have four processes in system RAM at the same time. It's more efficient. It doesn't get any functionality, but it is faster and way more efficient. Looking at how I handle devices, well, no direct access, including display, keyboard, storage, etc. Everything works with I/O streams, and I/O streams behave like queues. You put stuff in it or you read stuff from it, and when you try to write to it when there's no room, you get blocked. If you try to read from it and there is nothing there, you also get blocked. You can prevent that if you want. In that case, you will just get an error if you can't read or write to it. Also, all I/O must be buffered. Hardware will be handled when the kernel has time for it. It will put data in a buffer, and a process can pick it up. And devices are handled by dedicated threads in the kernel. Well, With that, I would like to show a few things, just a little bit. Let me switch to this, and let me actually start the system. This, by the way, is another project of me, that's Device Manager, which some of you may know. I have the luxury of being able to integrate extra software in it, and one of them is C128. This is the boot time of it, which is like 3 seconds. First thing to show is I have multiple consoles, so I have 1, 2, 3, 4, and a console with debug output. And one of the things that you see here is that there are two things running, one handling the ultimate command interface to support the Ultimate 2 Plus card, and one running the IEC interface, or the Commodore serial bus. And you also see 4 times a read line process. I will show what it is. And all of those reserve buffers. And those buffers all come from a shared bit of memory. So going back to console 1, I have a PS command which shows you the actually running tasks at the moment. And you see 4 times a mini shell. A mini shell lives in the kernel. It is a very, very tiny shell, but it's what I'm using now, and it knows a number of commands. It can actually parse command line arguments, and it provides everything to build a much bigger shell. It just doesn't provide many commands. So we have time, uptime, and what so on. Looking at the processes that I have here, you currently see there is a mini shell. I can start a menu which has a few demo programs. And if I now switch to another console and type PS, you can actually see that one of the tasks that is running now is the menu. Switching back to it, I need to switch back to the right console. I can run this well-known demo. Anyone who ever watches 8-bit show and tell has seen this, and many who don't also have seen this. And if I look at the running processes now, we can see it in there. If I start the menu here as well, I can start a counter, and we can see it's now at 200 something. We have here the 10 print demo running still, and I will leave that running for a little while. And switch back, and we see that the counter is now at a much higher number because it kept running in the background. Since I'm a bit low on time now, I see, I'm going to show one more thing, and it is how responsive the system remains. Let me start the menu and not with an argument. I have a thing in here, let me see, yeah, option 6. What does it do? Well, it actually tries to start as many tasks as possible, and it keeps doing that in a loop, and each task is just printing its own ID. If you look, meanwhile, the counter is still running. Going to yet another console. Let's see. Yeah, that one is also still running. Going at another console, we can see that there are many, many tasks running now. And if we look at the debug output, we can actually see when the various processes are starting and stopping. So that is basically how far the system is. I/O is partially working. Storage is, well, I/O is working for the display, for the keyboard. Storage is partially working, and that is the current part that I'm working on. Switching back to my presentation. Let's see. There we go. Yeah. So people keep asking a number of questions about this. And one is, will GRAM or rambling work as memory expansion? Currently not, and it can't be used for swapping, but I may support them to provide extra RAM to applications. That depends a little bit on how much room I've left in the function ROM. I already mentioned 256K system RAM is supported, and actually gets you an advantage. And well, only 2 processes. Well, actually, you can run many more processes, but you need a RAM expansion. You need to swap them too. And if you have 256K system RAM, you can run 4 processes from RAM directly. Can it run a regular C128 applications? No. However, the Commodore jump table is there. And that means that porting Commodore 128 applications that just use the kernel and only use the kernel jump table, yeah, that shouldn't be too difficult. And last but not least, why? I mean, what is this good for? Well, depends. The first thing it serves is my curiosity. I was actually curious if it could be done, not just in theory, but if it would work and if I could really make it responsive. I already did show to myself that I can. But now I need a real purpose for it. And one of the things that it could be really useful for is, for example, to combine it with a BBS client. So you can have a file manager running in one session. You can have your BBS session. You can download files. You can meanwhile connect to a second BBS if you would like to. And you could also manage files that you just downloaded or look for files that you want to upload, copy them to the right place, and so on. So yeah, usefulness is a bit of a question, but that's what I envision as one of the things that it could be used for. One thing I don't mention here, is it available? Every so often I do release a preview version. I will call it the preview version until I at least have storage support. And I released that in the C128 enthusiasts group on Facebook. Eventually, I will also make the source code available. Same applies the moment I actually get storage working in a way that I like, so that I am not changing things all the time while people are trying to understand the source code, because that is a bit nasty, I think. Yeah, with that, I am at the end of my story, and I would like to thank you for the attention, and I would like to thank the Commodore user group for the opportunity to present this little story. So that's it for me.
Yes, many thanks, Bart. Let's see if we have any questions. I saw a comment passing by, a comment from Andre. I think that's what, at the moment you were explaining that that then you copy from one RAM bank to this to the expansion unit, and then he refers to that point. He says that's also a lot of copying, because I think before you referred to another system that was also doing quite a lot of copying. Maybe I don't know, Andre, you want to comment more on that, or was that a question behind?
That was actually the question, because you mentioned that switching processes on the stack means copying a lot of data around on the stack, put the stack somewhere else, and then copy back the other stack. But on the other hand, you only have 2 processes in memory, and the other processes are all running in the RAU, and if you switch them, you have to copy much more data. Isn't that right?
That is correct. There are 2 reasons why that is more acceptable than what Linux does, for example. First of all, I only have to do this between processes, and within a process you can have multiple threads running, and I don't have to do this for each thread. So if you, for example, would consider a file manager, you select a number of files and you say copy those to another destination. The copying could be handled by a thread, and you can get back your user interface and browse to another directory or do whatever in it that you want to do. And the system switching between the copying task and the user interface task does not involve swapping to the REU. So yes, it has to happen, but it doesn't have to happen all the time. The second thing is that copying to and from REU is really an order of a magnitude faster than copying with the CPU from memory to memory. So looking at performance of copying of a lot of RAM, the REU can simply do that a lot and a lot faster. So in that way, I prevent the huge impact that copying RAM can have on a system like Linux.
Thank you.
Could I ask a question?
Yeah, sure.
You had processes that print stuff running in the background.
Yes.
And what happens with their output? Do they detect that they can't print anything, so they have to have code for that? Or they print and it's thrown away, or what happens?
They don't have to know about that. When they print to the screen in this case, all they really do is write to a buffer. And there is a task running in the kernel which looks at all the different buffers, and each buffer can be tied to a virtual console. So when there is data in the buffer, the kernel will just copy that to the right memory locations and leave it at that. If I switch between consoles, let me see if I can bring that back. Yeah. Let's stop this thing. Each console has its own bit of a video RAM. So this console is located at address 0 in VDC RAM, and this one is located at address 2000 in VDC RAM. And so the kernel can just copy it to the right place, and the task that is printing to the screen doesn't have to know about it. And the same applies to the keyboard. When I type things on the keyboard, the system actually looks at what console is currently active, and it will put the keyboard input in the right buffer for that console. And the process that is attached to that console will eventually get that input.
So this will only work with the 80-column display then, right?
That is correct.
Yeah. But so if you have a task that is printing stuff, and then you switch to some other task, and the background task prints 2 lines of text, and you switch back to it, those lines are now visible on the screen.
Yes.
Excellent. Thank you.
That's what we can see here, actually. I mean, this is this is one console, and this is my counter. And if I just switch back and forth between 2 consoles, you can see that the counter changed in the meantime.
Yeah, but it wasn't evident to me if it was actually printing all the time or if the output was discarded while you weren't watching it.
No, it's not discarded.
Okay,
it is printing all the time.
Cool.
And when the buffer is full and there is no time to write it to the screen because something else is really keeping the screen busy, that task will temporarily block. It will just not get any time slices. And actually, when it blocks, it will tell the system like, hey, I tried to write to something and I have no space. And the task the time slice will immediately end at that moment, and that the remaining time will be returned to the system to run other tasks. And the system won't schedule that task until there is actually room for it to write to again. So eventually, what you mentioned, will the task be stopped if it's in the background and it can't write anymore? Yeah, eventually that will happen. But in the background, the kernel will also try to empty that buffer whenever it gets time. And emptying those buffers actually has a very high priority, which we can see if we look at this overview of tasks. You can see there are cons 1 to 7. And the one that is currently at in the foreground actually has high priority. And let's see, do I say that right? One has high priority and the other one should have a normal priority. So the one that is currently in the foreground actually gets a bit more priority also.
Just want to say this is really, this seems like a really impressive project and surprisingly responsive on a 2 megahertz machine.
It is. That is, yeah. When I started with this as just really a proof of concept, I was really surprised by how responsive it was. And that's also why I continued trying to expand it into a real system. Yes.
One question, sorry. The ps command you're using, is that built into the shell or does it load from storage? It's built into the shell.
Yes, it is. All the commands that
Makes it very snappy, that's right.
Yeah, all the commands it currently has are built in. So if we, typing is difficult because actually my screen is delayed. That is kind of, all those commands are just built in. And it can also run commands from disk, except for one slight issue, that is that storage is not reliably working yet. I have a few bugs still in the storage handler, which make it crash when it finishes loading something. And that is a bit nasty, so yeah.
Thanks.
Okay, any other questions?
I had a couple, but you answered them right now. I was looking at this load 100%, and I was just wondering how does it handle when there is just no time. But you just answered that, so thank you for that. Maybe the other one I saved as a question was, you mentioned at the beginning that you would consider supporting Jiffy DOS, but in practice, how would that work? Because then I think that there you need the disk, you need this, you need the RAM. How would you see that?
Yeah, you will need the proper ROM in a drive, but there exists a project called SGDOS or Soft Jiffy DOS. Sadly, the website behind it, H2 Obsession, is no longer around, but I was lucky enough to save the source code for it, and that is open source. So at the moment that I actually have the source for this project released, I can also integrate the code from H2 Obsession and integrate their SGDOS code, which allows me to support Jiffy DOS without actually needing Jiffy DOS ROMs in the computer itself. Which brings me to one thing I didn't mention really. I do not use the Commodore kernel for anything. So in theory, I could turn this into a kernel replacement if I really wanted to. It does not use kernel for anything.
Okay, great. Many thanks, but I don't see any more questions in the chat. I'm looking on Facebook neither, but I guess like usual, if someone has a question, they can still post it in the chat. So thanks again. I will stop the recording now.
Okay.